In this video, we present our approach to rendering synthetic objects into real scenes using image-based modeling and rendering, global illumination, and high dynamic range photography. The first component of our approach is to illuminate synthetic objects with real light. One method for recording light looking in all directions is to photograph a mirrored ball, such as this one, which sits on a kitchen table. Unfortunately, cameras lack the necessary dynamic range to make useful measurements of incident illumination. In this image, the light sources are completely saturated to white, making it impossible to gauge their intensity and color. We can recover accurate measurements of incident illumination using the high dynamic range photography technique presented by Debevic and Malik at SIGGRAPH 97. Using this technique, we can combine pictures with varying exposure times into a single representation that accurately records the intensity, color, and direction of all forms of direct and indirect illumination. Once the incident illumination is recorded, it can be used to illuminate synthetic objects with a global illumination algorithm, such as Greg Larson's radiance system. This rendering shows a collection of objects with a wide variety of material properties illuminated by the light from the kitchen. The objects properly reflect each other and exhibit the appropriate soft shadows, reflections, and caustics. Using a different map of incident illumination gives a different quality of light to the objects. This illumination, shown in the upper left, was acquired on an overcast day beneath an outdoor trellis. We can construct a simple light-based model of the kitchen by projecting the recovered radiance values onto a geometric model of the room. This allows us to place the synthetic objects into the same space as the original environment. In this animation, we see the synthetic objects placed within and illuminated by the light-based model of the kitchen environment. While the light-based model is low resolution and suffers from uneven sampling, we can begin to sense the objects existing within the same space as the kitchen. Here we can observe the same objects illuminated by the overcast outdoor environment. This next animation shows a different series of objects illuminated by the kitchen environment. Here, the high dynamic range nature of the renderings is accentuated for visual effect through a combination of duotone mapping, image defocus, and artificial vignetting. This last animation shows a collection of synthetic objects rendered with light recorded at the eucalyptus grove on the UC Berkeley campus. The environment used was created from two light probe measurements taken 90 degrees apart to provide even sampling and to remove the appearance of the camera. To be fully general, it is necessary to not just illuminate the synthetic objects with the appropriate light, but to have the objects cast the appropriate shadows and reflections in the scene. Suppose, for example, that we wanted to render our synthetic objects onto this background plate photograph of a table. We first use a calibration target to record the camera pose relative to the scene, and acquire a light probe measurement in the vicinity of where the synthetic objects will go. As before, we use a simple light-based model of the environment to extrapolate incident illumination conditions. The camera pose and lighting information allow us to render the objects into the scene with the correct perspective and illumination. In order to cast reflections and shadows on the scene, a stand-in for the local scene of the objects is created. In this case, the local scene is a rectangular patch of the table. Methods discussed in the paper were used to estimate the local scene's material properties. Unfortunately, the local scene is not a convincing rendition of the table. Because both its material properties and incident illumination are only estimates, its appearance is not consistent with the distant scene. We can improve the consistency using differential rendering. In differential rendering, we first render the local scene, illuminated by the light-based model, without the synthetic objects. We compare this appearance to the previous rendering to isolate the effect of adding the objects, creating a difference image. Dark areas in the difference image indicate where the objects create shadows, and bright areas indicate where the objects create reflected or focused light. Finally, we use this difference image to modify the background plate. In this case, the result is visually consistent with the existing background, despite the approximated material properties and incident illumination of the local scene.